Beleza. Vamos começar a reunião de grupo. Dessa vez de forma diferente, tá? Fazendo uma live aqui para já estar gravado já tudo no YouTube. E assim vocês podem ter acesso facilmente, tá? Ao conteúdo. Vamos lá, pessoal. Já mandei o link para todos vocês. Então, vou compartilhar logo de cara.
Oi.
Oi, Clarissa. Tá me escutando? Bem?
Estou escutando.
Beleza, então já vamos começar, tá?
Vai fazer em português mesmo, né?
Vou fazer em inglês.
Beleza. Porque eu achei que,
Tá, só
porque como ia participar muita, talvez, gente do grupo lá de divulgação.
Acho que vai não, ninguém vai participar não, acredito eu.
Tá bom.
Pelo menos ninguém entrou em contato dizendo que ia participar. Vamos lá. Okay, all right, everyone. So let's get started without further ado. In today's group meeting, I'm gonna present a paper from archive, a recent paper. Well, not quite recent, from January, but the topic is quite hot. So let me share my screen with you. Just a second. All right. So can you see Clarissa on my screen? Clarissa, can you see my screen? Well, I'm assuming so. So this is the paper that I'm going to talk about today. Is about the Galactic Center access that has been observed by Fermi satellite, and this access has been firstly observed in around end of 2010, and then since then we have been collecting data, and the significance of this access has increased over time. Okay, so as you can see here, so this is a paper from Mattia D. from Turin in Italy. And instead of just going through the paper step by step, I'm just gonna go share my some notes with you so you can all understand what this paper is all about. Okay, so now I'm gonna share my board. So what's this Galactic Center access? So let's say that we do have the Milky Way. Okay, so in our Milky Way we have the Galactic Center. Let me just write in a second. Okay, so let's say this is part of the dark matter halo we have, and this is the Galactic Center right here at the end center, and then this latitude and longitude, or the other way around. It doesn't really matter. Usually that's how we do it. Let me E and L. And this region here, let's say from here is around 5 degrees, and from there also 5 degrees, roughly. So, from the center of our galaxy, we have been observing gamma rays, which represent an excess over the gamma rays we expected from astrophysical background. So that was around 2010, okay? And that was first observed by Dan Hooper. I'll put N et al. Because there were many other authors following up that paper that also observed the same axis. At least good enough. That was the very first original paper in 2010. Anyways, so we do observe gamma rays from the Galactic Center. So what? Why I'm talking about this? The reason why I'm talking about this is because the flux from dark matter should grow to with the number density squared of dark matter particles in our galaxy, right? So because we have dark matter annihilation, so we have pairs of dark matter particles, so we need two. That's why we have n squared, where n is the number density of dark matter. That's what we should have. It should be proportional to this. Should be proportional also to how strongly those annihilations are happening. So I'm gonna call this sigma v, which is just the annihilation cross section, right? And should be proportional to the number of photons which are produced per annihilation, which is called dNdE. So this flux, so as the number density for non-relativistic particles, rho is n times m, therefore n chi is rho over n. Okay, so this expression over here, I'm gonna use it instead of n, and then I'm gonna write this as rho chi squared over n chi squared. So as this flux, we are observing, we are a satellite or a telescope, we are observing the galactic center right there. We are pointing the telescope to the galactic center and we are observing gamma rays. So the way we do is, in order to account for the total flux coming from this line of sight, we have to integrate over the line of sight for obvious reasons. Therefore, this flux should be integrated over the line of sight. However, for the purpose of this group meeting, I'm gonna call this whole thing, which is related to astrophysical properties of the signal, rho chi, and this dNd, I'm gonna call this some factor C in name of after Clarissa. Okay, so this is the factor of Clarissa. And therefore, so let's say that we know factor of Clarissa, and the only thing that I don't know is the sigma v and the mass of the dark matter particle. And tá, pode deixar aí, eu tô numa reunião. So we don't know the sigma v and the mass. Therefore, if we know the factor of Clarissa, the only thing I don't know is sigma v and the mass, which are particle physics quantities. That said, so the flux of gamma rays stemming from the galactic center should be determined by the sigma v and the dark matter mass squared. Therefore, a guy, let's say a guy here, if here like this, called Jacinto, he does observe and collect these gamma rays for us. And he says, look guys, the flux is this value. The flux should be a function of energy. As you can see here, we have this dNd, which is n is the number of photons per energy produced per annihilation. So Jacinto said, look, Farinaldo, the flux I've measured is this function of energy. Okay, fine. Then I compare this flux is a function of energy with the dNdE, with the expression I just showed you up there, over here. And I said, okay, what should be the sigma v and the dark matter mass in order to have a flux consistent with the measurement? In that way, I can trace, or in another way, determine what is the region of parameter space where sigma v and dark matter mass combined are consistent with the flux. Since it's a ratio, we have the flux here. This flux will convert into a plot in this plane, sigma v versus mass, which will look something like this. And the reason it looks like this is because this region here, as you can see, grows up quickly. And the reason why it grows up quickly is because as the dark matter mass grows, which is this plane here, is in this direction, and the sigma v is increasing in this direction. As the dark matter mass increases to the right, the flux decreases. As the flux decreases, the amount of gamma rays produced from dark matter annihilation gets smaller and smaller. Therefore, my sensitivity to detect this signal from dark matter, from heavy dark matter particles, is weakened. Okay. And the reason why usually the plots have this feature over here, which with this sharp weakening of the bounds, comes from the fact that every single telescope or experiment has a limited range, energy range, which they are focused on, or the apparatus is designed to probe gamma rays for a given energy region. Therefore, so for instance, if you produce too heavy dark matter, if you have too heavy dark matter particles, you produce less gamma rays because that's the formula of the flux. However, if you have a too light dark matter particle, even if the flux increases, but your experiments, your apparatus is set up just to probe gamma rays for a given energy window. Therefore, you won't be sensitive to that gamma ray anyways. So that's why we have usually plots that look like this. Oftentimes the collaborations, they don't plot the whole thing like this. They cut because the bound here just goes up so quickly, weakens so quickly, that they don't report this region here. They just cut the plot and say, look, my bound is this one. And they start this plot from that region over there. That's why you just see weakening, sort of, not linear, but sort of linear weakening of the limits from gamma rays. And the same thing I'm telling you is also not quite the same, but sort of similar to cosmic ray searches. So that's the whole idea, okay? So why I'm talking about this? Because since 2010, we have observed an axis of gamma rays. And the same way I'm telling you that we can sort of outline the regional parameter space where sigma v and m chi reproduce the flux measured. If we do observe an axis, we can also derive a regional parameter space in terms of sigma v and m chi that reproduces the axis observed. And that's what happened since 2010, roughly. And the regional parameter space they derived is something like this, a blob like this. They say, look, if you live over here, okay, so if Jacinto lives over here, all this regional parameter space can explain the axis, the gamma ray axis observed. This gamma ray axis observed by Fermi is around 0.3 GeV up to few GeV or so. It's picked around that number in energy, from 0.3 to around few GeV. So that's the peak of the flux of the energy spectrum, if you say. So if you do have a dark matter model which you want, or you, for some reason, you're designing your model to fit or to somehow reproduce the gamma ray axis, you should have a model where the annihilation cross-section of the dark matter particles you have and the mass of the dark matter particle should be around that range. And that, which range is that? That goes from roughly 20 GeV to say 45 GeV or so, around 50. And the annihilation cross-section is around 10 to minus 26. So this here is that window there. So if you have a cross-section around 10 to minus 26 and dark matter mass between 20 to 45 GeV, you can potentially explain the axis. The problem is not explaining the axis. So why I'm talking precisely about the paper? So why I'm motivated to talk about this? So we have seen this since 2010. So why I'm talking about this now? So the reason is, so far we have, that's how science works, right? So we have observed the axis, and then the cross section that could fit the axis was very high. And then as we understood, we collected and collected more data with Fermi, we could understand better the astrophysical processes that could result into gamma rays. And therefore, that left less and less room for dark matter annihilation to take place. And in that case, what happened is, if you just do like a back of envelope calculation, let's say that that's the number of photons I measured, and then the total number of photons is number of background photons plus number of dark matter photons from dark matter. So as this thing is measured, I measure this value, let's say is 1000. And this thing, as I understand better my background, this number of background photons increases, the number of photons from dark matter particles should decrease, right? So I measure 1000 photons. And therefore, if the number of photons from dark matter should decrease, and then that's roughly the flux, right? So you go up there, if this flux here has to decrease, means that this ratio, dark matter sigma v and m chi squared, should decrease. So, and that's exactly what happened with time. So firstly, when we did observe this axis, the favorite region to explain this axis was right over here. And then with time came right over here, and then with time right over here. And that's where we are today. So it sort of shifted a bit by not that much, but it shifted down a bit. And that's how science works.
Sorry, Fernando, this part was not so clear to me. Could you repeat, please?
Yeah,
this
sure.
Part of the background and.
Yeah, so the number of photons, let's say that I measure 1000 photons coming from the galactic center, 1000. And then that was in 2010. And then Clarissa, with her background model, said, look, for now, my background model, the way I understand how physics works, should give me 900 photons. And then I say, okay, so if you're saying your background gives you 900, the number of dark photons from dark matter should be at most 100, right? So let's say around 100. But with time, Clarissa evolves, right? So he gets better and better and better. He gets better understanding of what's going on, and said, look, actually, Farinaldo, with my current data I have, the gamma rays coming from the galactic center should not be 900, actually is 950. So I should expect 950 photons from the galactic center. And so, okay, so now I don't have freedom for 100 photons. I should have a freedom for 50 photons. If I decrease by a factor of 2 the sort of the flux from dark matter, that will impact on the sigma v in dark matter mass I should have to give me the 50. Before I could have a 100, now I shouldn't have 50. So my sigma v over the mass will change, right? Will also decrease in order to give the 50. And if Clarissa with time finds that actually it's not 950, is let's say 980, then again, my number now should be 20. And again, my sigma v should be also smaller. So that's how it goes, okay? And that's exactly what happened. Okay, so the reason why I'm talking about this is that the axis we observed with 11 years since 2010 to now, with 11 years of data, what we have observed so far is fully consistent with dark matter particles annihilating in the galactic center. And the profile, the morphology of the spectrum is all consistent with the dark matter models that we sort of have, right, with the WIMP miracle also. The most difficult part of having a dark matter particle that could fit the galactic center is having that model also be free from existing constraints rising from a variety of data sets. So if you want the dark matter model to explain a real, perhaps is a real thing, the access is there. Whether it's dark matter or not is a different story. But perhaps it seems so. It seems to be. But there are also competing solutions for the access, which are pulsars. But this is a time for a different discussion. So if it is dark matter and you want to explain this access, then you need to have a model to explain the access through annihilating dark matter, for instance. There are other alternatives out there. So you want to explain the access, but you also want to, your model, on top of explaining the access, has also to obey all existing constraints. Because if your model just explains the access and is ruled out by other means, so whatever. So your model means it's not a real model. It's not a plausible solution to the Galactic center access. So, and this thing, for instance, when around 2014 or so, there was a boom of papers regarding dark matter models to explain the access, because there was several papers that confirmed the existence of the access and the possibility of explaining the access through dark matter annihilations. So there was a boom of papers in 2014. Since then, from 2015 or so to now, there are not that many papers trying to explain the access, not because it's not interesting, but simply because people have exhausted all the possibilities, all the solutions to the Galactic center access. It's not because it's not interesting. It's very interesting indeed. Okay. So that's basically what I had to say today. If there are any questions, Clarissa, could you tell me? No? All right, so that's all I had to say. I think that was about for the group meeting, going quickly through a paper. So I said 20 minutes. I was roughly that. So I
finishing now?
Yeah.
Okay. So there's a question, yes.
Okay, tell me.
The question was from Tessio. What is the range of masses Fermilati is sensitive to?
So for dark matter, well, it depends on the channel, but it's sensitive. We cannot really say the mass, but for instance, if Fermi is usually sensitive to gamma rays from roughly 100 MeV to a couple of hundred GeV. So usually they say from 100 MeV to 100 GeV. That's usually the energy range which they focus on, but they're shared. For instance, you can extend a bit further from that. So it's, let's say, from 100 MeV to further, a little bit further than a couple of hundred GeV. So usually that's the energy range which they focus their dark matter analysis on. So from 100 MeV to, let's say, 100 GeV. With the dwarf galaxies analysis, which is something completely orthogonal to this one, regarding the astrophysical object, which is being analyzed. That's usually the energy they quote. So look, we are analyzing our data from 100 MeV to 100 GeV. Does not mean the mass, okay? Because if you have a dark matter mass, even if you're probing gamma rays from up to 100 GeV, you can probe dark matter masses with 400 GeV, because a dark matter particle with 400 GeV will, when annihilates, will generate low energy photons that will fall into that energy ring window. Okay.
Do you know if there is some other experiments that tries to distinguish the background from the galactic center that could give some more information, interesting information from the background about for that region?
Yeah,
because
our hope
I was wondering, yes, this point.
Our hope was CTA. But CTA will not be able to probe this. The energy window is too small for CTA.
Yes.
So I don't think we'll have, well, I don't know of any experiment that has been approved already that will be capable of, let's say, replacing Fermi legacy.
Yeah.
I don't know. So unfortunately, this will just be there.
Yeah, yeah. Because if we don't know what's exactly the background in that region, how can we say exactly what we can expect from there, right?
Yeah, I mean, only if we have, it's very hard to extract the and understand completely the background from the Galactic Center, because I mean it's
Yes,
the
it's
Galactic
really
Center.
hard.
So,
Mm-hmm.
but yeah, I don't
I
know.
have.
This I think is this access will stay there for, we will last a very long time.
Mm-hmm. There's another question here from Tessio. Are there models that simultaneously accommodate the Fermat access and now also the positron access from AMS?
They are, but not with the same dark matter candidate, because they fall into completely different energy windows. So one is, let's say, few GeV, the other goes, is like, I'm trying to remember the, I think it's the latest peak of CMS about a couple of hundred GeV. So you cannot fit the same axes with the same dark matter particles. So you have to have a model with a multi-component dark matter in order to fit them. It's already hard by itself to fit the AMS axis. Imagining fitting both axes is quite hard.
Mm-hmm. I have another question. Do you know if there is nowadays some bias related to what can explain the access, like it is much more like pulsars or much more like dark matter to
Well, the
explain the
community, I would say that
HEV
the
access?
consensus of the, I would say that most of the community believes that the most likely answer are pulsars. So nearby pulsars that fall below the threshold of Fermi, below the detection of Fermi, are likely the explanation for the Fermi axis. But there's a part of the community that they still believe it is dark matter. So
Mm-hmm.
I'll say that now more people are convinced there are pulsars than dark matter. But the way, I would say, we could conclusively say that we don't know.
Mm-hmm. Yeah. I have another question from Alvaro here. Considering the errors from this kind of experiment, is it possible that this access could be from another sources besides the annihilation, or it fits the data completely? It
Different from
seems,
pulsars and dark matter? I don't think so.
yeah, I don't think so.
No, it's not any pulsars. It should be nearby pulsars, because there were some pulsars in the past. They were used to explain some of the AMS access in the past, and the energy spectrum they had was very different. Could not fit the AMS access, and the pulsars we have, they are not also capable of explaining the access. Should be pulsars that have not been detected so far. So, um, but it's still, they could be a plausible. They are a plausible solution, but it's still, we haven't detected all these pulsars, this population of pulsars that could explain the access. So,
Mhm. And Farinaldo, I have another question. How about the TV access observed by Has? No one talks anymore about that. It seems like, I don't know if anyone believes on that or.
no, so there was a pivotron that has been observed by Haas, and that has nothing had nothing to do with dark matter. There was one very in the back there in the old days,
Yeah.
a TV access from has, yeah, it didn't get momentum, I would say. So not
Mm-hmm.
many people were very interested in that, and I don't know, I don't dare to say the reason why. Why?
Maybe CTA could give some clue
In
about
that
this.
case, yes, yeah, CTA
Yeah,
would
because
be
it's
perfectly capable of
isn't the
shedding
TV.
light on this access. Yes.
Mm-hmm. So I cannot see any more questions. So I think we can finish here. If I'm
All right, so good. All right, I think it worked. So having 20 minutes of each talk. So prepare yourselves. So let's see who is going to be the next one. I believe it's Jacinto. Jacinto is going to be the next one to present like this, Jacinto. So gives less work. It's already uploaded on YouTube. We don't need to download and upload again. It's on. All right. So thank you for your time.
It's a
Bye.
good idea. Thanks. Bye bye.